So in chapter 25, I'd like to examine Gauss's law, specifically one of Gauss's formulas, which is finding the electric flux through a closed surface. And we know that that formula is simply the closed integral of a surface, the charge enclosed in that surface multiplied by the derivative of the area of that surface. So we'll get more into that later about the significance of that equation. So say we want to find the electric flux going through the sphere here that encloses a charged positive Q. And you can see here the field lines point radially outwards, so those field lines are going to permeate the surface of our sphere here. So we can say in this case that the charge is going to be constant, Q is not going to change at all, so we can actually pull that outside of the integral. That makes things a lot easier because now we're just integrating the derivative of the area function. So that just becomes the area function. Therefore, the electric flux going through this sphere is just going to be the Q enclosed times the area, which is a very simple equation and you can find. Therefore, Gauss's law applies here. However, in our second example, we have an open box that has a positive Q charge in it. Now, everything was going to work the same. However, Gauss's law does not apply here because this is an open box. Gauss's law only applies to closed surfaces. All those field lines are going out of the surface. They're not permeating anything through the top. So this is not a closed surface. We can't use open box like this example here. So that leads us to the significance of Gauss's law. Well, what's so important about it? Well, we want to find the electric flux through something like, say, a sphere. Well, the equation tells us that it's the closed integral of E times dA. Now, if you try to calculate that by hand, you know that finding the Q force that goes, or the Q lines that go through the surface of the sphere go through every point infinitesimally distances, small distances apart. And if you had to count those all by hand, that would most likely be impossible. However, Gauss's law simply puts it in a simple form for us that we can equate, saying that the Q enclosed multiplied by the integral of the derivative of this area is going to equal our electric flux, instead of having to count each area, infinitesimally small area by hand, and multiplying it by that Q enclosed.